Hey there, my name's Ryan. We're going to go over how to get the differential kinematics from the Niryo One robotic manipulator from Coppeliasim. So first things first is we're going to set up the scene. This one's already set up, so I'm going to open a new one. Go to File, Open Scene, File, New Scene. I'm going to go ahead and close out of this scene. Alright, so the Niryo One has 6 degrees of freedom, but in this example we're just going to be manipulating 3 of those degrees of freedom. So we are going to be looking at this joint here, and then there's another joint that twists the end effector around the end that we're also going to be taking a look at. So first things first, we can click the plus button next to this Niryo One egg-shaped icon, and it'll basically list all of the different components of the robot. We are going to get rid of the cuboid, the gripper, and the Niryo One connection. That way all we have really here is all of the links. Next thing we're going to do is we're going to open up this little script button right here, click the child script and disable it. And we're going to create our own script. So we're going to click on pretty much any one of these components. I'm going to click on the Niryo One joint 1. We can right click on it, click add, and then go to associated child script and non-threaded. Once we do that, it's going to have this little script icon to the right of it. We're going to double click that and it'll pull up the code for that script. All we're going to do is add some text to the top. It says sim remote API.start 19.999. This is going to enable us to connect to Python later on. Alright, the next thing we want to do is we want to take a look at each one of our joints and make sure that when we double click the joint icon and go to Show Dynamic Properties dialog, we want to disable the control loop and lock the motor when target velocity is 0. That way when the target velocity is 0, nothing else moves. Everything is dynamically enabled, so if you don't do this, things will move even if the motor is technically off. And we're going to do that with every single one of these links. Sorry, joints, not links. Alright, now that that is set up, we're almost done. We're just going to need a dummy object in place of our end effector. This is required so that we can figure out the velocity of the end effector at a certain point in time during our code. To do that, we're going to go up here to Add, click Add, then Dummy, and then we're going to drag this dummy down past the Niryo One joint and connect it to the Niryo One link 6. Then we're going to have to rename it because in the code that I'm using, we named it end effector, so I have to rename it end effector. To do that, you just double click on the text, then type whatever your new name is, and then you have to click enter in order for it to stay there. If you don't click enter, it'll just go back to its original name. Now we can see our dummy is right here. Obviously we want it to be somewhere up here where the end effector would be, so in order to do that, we're going to make sure end effector is highlighted, go up to this position icon, make sure we're in the position tab, make sure that parent frame is circled in, and change all of these to 0. What that does is it moves the end effector to the center of its parent frame, which would be the center of this link 6, and therefore where the end effector would be attached to. Once that's done, the robot is pretty much ready to be simulated. What I am going to do right now is just to make this a little bit more visible. I'm going to double click the end effector, change this to 0.02 to make it a little bit bigger, and adjust the color. Let's make it a nice purple. Okay, so now we can clearly see where this end effector would be as far as the rest of the manipulator. Now, if we go to the Spyder code, I'm going to go through each portion of this code, and then I will show you how we derive the differential kinematics by hand. So the first part of this code just imports some packages that will allow us to connect to Coppeliasim. And then this little bit of code actually will connect Spyder to Coppeliasim and enable us to be able to work with the simulation directly. This next chunk of code is really just some bookkeeping code. So essentially we set up 6 joint variables here to connect to each of the respective joints in the actual simulation. So the Niryo One Joint 1 is the name of the joint in Coppeliasim, as you can see here. And then we set that equal to a joint name that can be used in the rest of the code. And then we do the same thing with the end effector. So now we essentially have variables referencing all of the joints in the simulation as well as the end effector dummy. The next part of the code uses the command simx set joint target velocity. What this part does is exactly what it says. It just sets the velocity of these joints in their respective rotational directions. And initially it sets them as a negative value, so there's 0.04, 0.04, and 0.05 for the 3 respective links that I had mentioned earlier. Then it waits 1 second, sets all of the joints back to 0, and then sets them back to a positive value equal to the magnitude of what was before. It sets that for approximately 0.87 seconds. The reason that we set it to a negative velocity, then set it back to a positive velocity, is so that during the simulation, it can get back to its approximate same position that it initially started in. The reason we need that is because the differential kinematics that we calculate by hand are based on the robot being in its initial orientation, so it being straight up and then straight over. What we'll see in the simulation is that the robot doesn't actually end up in this orientation at the end, therefore there is going to be some error in the velocities that we get with the differential kinematics that we do by hand versus the differential kinematics that are found using Spyder and Coppeliasim. So the next part of this code finds the position of each of the joints that matter. So joints 2, 3, and 4. We need to find each of those positions as well as the end effector position to be used in deriving the differential kinematics by hand. These are really important to get from the code itself because the code may not be using the same world frame as we set up in our diagram, which I will show later. So we need to know where they are in the actual world frame of the simulation. That way it's directly comparable to the simulation's results. The last part of the code does the most important part, which is actually figuring out what those linear and angular velocities are for the end effector. So that's what this code does, the get object velocity. Now keep in mind, this is definitely something that I struggled with, is that it finds the linear and angular velocity with respect to the world frame. So you're not finding it with respect to any joint frames or link frames. It's with respect to Coppeliasim's world frame, which you can see in this bottom right hand corner has this XYZ orientation, and then it doesn't actually show where it is on the floor, but it does have this XYZ orientation. Now the robot is initially sitting on the floor, So what I am going to do is I'm going to move it to the 0, 0 position in the X, Y direction. So we're going to click this, go to our position, go to the world frame, and change this to 0, and change that to 0. So now this should be centered in the floor. Just makes it a little bit easier to see where everything's at. Alright, so let's go back to our code. The very last thing the code does is simply just stops the robot. So it'll stop approximately in the position that we find all of these values for. So let's go ahead and make sure it actually works. I'm going to move this over to my other screen. So the way we actually do this is we're going to press play up here. It's not actually going to do anything because the code hasn't been press play. And then on the code, we're going to press this button and it should start moving the robot for the simulation. So I went ahead and pressed that. So it's going to move down and then move back up. Essentially just simulating it, picking up something and putting it back at the same height. Now as you can see, from looking at it directly on, you can see that this link is no longer going straight up. This link is no longer going straight to the right. And that's why essentially what we're doing is a rough approximation when we do the differential kinematics by hand. Now if I click the stop button, you'll see it actually go back to its initial position. So now it should be straight up again. So the times that I've chosen here, this 1 second in the having the negative values for the velocities and the 0.87 seconds is really just an approximate time to get it back to that initial orientation. So after that's done, we can go into Variable Explorer, and all of these variables will be defined. Most of these are just defining the joint variables. But as you can see down here, we've got position 2, 3, and 4, as well as the linear velocity. So this is the linear velocity of our manipulator in the absolute world frame. And then up here, we have the angular velocity in the world frame. And we're going to compare those directly to the derived kinematics that I'm going to show next. Alright, so this is the diagram that I used to approximate the final position of the end effector when it's moving at 0.04 radians per second, 0.04 radians per second, and 0.05 radians per second in joints 2, 3, and 4, respectively. So joints 2, 3, and 4, as I described earlier, they're all revolute joints. So joints 2 and 3 are going to rotate about the world's x0 axis, which is right here. So does joint 3, and then joint 4 is rotating about this z4 axis, which in the world frame is this y0 axis. Now again, this is just an approximation, assuming that all of these are in line with each other and at right angles. We can find the bottom values of the geometric Jacobian just by comparing the z values of the current frame compared to the world frame. So for Z2, for example, Z2 is going into the page, which is in the same direction as the x0 axis. So for the Z2 value in the Jacobian, we're just going to have 1, 0, 0 because it's in the positive direction of the x-axis. Then same thing for frame 3, it's also going into the page, so it's also parallel to that x1 axis, so that x1 term is going to be, x0 term is going to be 1, and the rest are going to be 0. Then Z4, as you can tell, is going straight to the left, which is in the positive y naught direction, so we're going to have a positive 1 in the y spot of this vector. Right, so the bottom of our Jacobian is going to be, sorry, these shouldn't be negative. It's going to be 1, 0, 0, 1, 0, 0, and 0, 0, 1. Now these are also important in finding the top part of the Jacobian. So the top part, we're going to take the values of the position values of joints 2, 3, and 4, which were found in the Spyder code here. We're going to take those position values and subtract them from the position value of the end effector, which is found here as well, to get the difference between the vector going from the initial point to the end effector to the link to the end effector. Once that's done, we multiply them by their respective z vectors here. So the top of the Jacobian for link 2 would be this 1, 0, 0 multiplied, taking the cross product of with the position of link 2 subtracted from the position of the end effector. And then same thing for all of these. So this is the difference between the position of link 3 and the end effector, and this is the difference between link 4 and the end effector. Once the geometric Jacobian is approximated, we can multiply that by the approximate input velocities, which should be 0.04, 0.04, and 0.05 to get these values for our velocity. Now, if we take these values and compare them directly to what was given in our Spyder code, right, our first three values are going to be the linear velocities. So the first value is negative 0.0014124. And this is compared directly to 0.00026. They're both pretty close to 0. This one does have the most error out of all of these values, but it's a really small value, so any variation is going to have a larger error. And then the rest of these have an error between 4% and about 15%. So 0.0059 versus 0.0066, still pretty close. 0.020 compared to 0.0187 is also pretty close. And then up here we've got 0.072 compared to 0.08 and 0.048 compared to 0.05. And then of course this bottom one is 0 and this bottom one here is also really close to 0, but obviously there's not like an error percentage that we can get from that other than 100%. So these are all the values that we calculated, and they're kind of far off, but it's a decent approximation if you didn't have the Coppeliasim simulation to figure out the orientations of all the links and the velocity of all the links and the position of all the links at that specific time. So if we wanted to make our approximation more accurate, we can use more values from Coppeliasim and from the Python code, such as the orientation values or the joint velocity values at the time where after this 0.87 seconds. So after this 0.87 seconds, if we found the orientation of all of those joints compared to the world frame, we could use those instead of the values that we use here as 100, 010, and 100 there. We can use that orientation to figure these out, and then that would give us a result that's a lot closer to what we should have here. And then the other thing that we can do is we can find the float parameter of each link's velocity, so their individual velocity, not their absolute velocity. Doing that would give us a better approximation for the input of this matrix here. So instead of just using our input values, we would actually use the values of the velocity in those of the joints at those times, which would make our result even more accurate. The main reason I didn't do that here is just to show that you can still get a decent approximation without using Coppeliasim or without using the different commands in Python. But Coppeliasim and Python work together really well to give us a better approximation given the dynamics of the system that the simulation has. Yeah, and that really covers everything for this video.